So, hello everyone. In this session, we are going to discuss very important topic, that is race condition. So, as I am reflecting with this picture, what is race is, we are very well aware about. Race is a kind of situation in real life, let's say, and number of persons are trying to achieve the same goal. And in which order they are achieving the goal, that order generates different result. So that means there is a race. If I say that, let's say this person is coming first and another person is coming second, and so on, and based on the order, the different prizes will be given to these persons. If there is a situation in whatever the order these persons will reach the line, the same prize will be given, so all will be getting gold medal. Then there is not a race, right? So a race condition is a condition when order of the execution of the processes will matter, right? So let's try to understand it technically. There are certain things you need to understand in case of race condition. So a race condition is a situation where the behavior of system or program depends on the order of concurrent event. So all the events are happening concurrently, right, or parallelly, and their order of execution is deciding the final result, right? The outcome of the program or system depends on the particular order of events or processes. Race condition can occur in any system or program involving concurrent access to shared resources or data. So this is important, shared resources or shared data. If concurrent processes are working on that, if we do not synchronize such processes, there can be a race kind of condition or situation. This includes shared memory or IO devices. So any kind of shared resource, maybe the memory or IO device. When two or more threads or processes attempt to access the same shared resource simultaneously, a race condition may occur. It's saying may occur, right? We'll take an example after that. A race condition can lead to unpredictable behavior of the system. The output cannot be predicted, or in different situations, the output may come different. Operating system and programs use synchronization mechanisms such as locks, semaphores, and monitors to prevent the race condition. So we will discuss these things in detail in coming sessions. Semaphores is one of the very important topic. Okay, monitors also we will discuss. Now let's take an example and try to understand what is race exactly. So you try to understand like that. Let's say there are two processes executing simultaneously. So let's say P1 and P2, two processes are executing. And these two processes are trying to update the same variable. Okay, so they are having the code, and let's say there is a variable you consider like count, and count variable is a shared variable which is being used by P1 and P2 both. So initially let's say count is having value 10. Okay, now so let me write count here. Count initially is having value 10. Okay, now here what is happening, P1 let's say is incrementing the value of count, and P2 is trying to decrement the value of count. Okay, now this line is written in the high level language like C, Java or C++. So this line will be converted into low level or assembly code or machine level code. So when this increment kind of statement will be converted into low level, actually this will not be looking like a single instruction, there will be multiple instructions, because assembly language doesn't support the increment operator, it doesn't have. So let's say if we convert this into the low level, so the very first thing, at low level we involve some registers. So let's say I'm taking register R1, and R1 first getting the value of count, so it is getting loaded with the value of count, and then register value R1 can be incremented. So let's say R1 plus 1 I'm storing in R1, and then finally the value of count can be updated like with the value of R1. Okay. Similarly, the P2 process can also do the similar kind of thing. So let's say P2 is incorporating a register R2 and it is loading the value of count, and R2 value is getting decremented by 1, so it is happening like R2 minus 1, and then the count variable is getting updated with the value of R2. Okay, so these are some of the statement. Instead of this single instruction, these are the instructions. Those need to be executed by process P1 and P2. Okay, and both the processes are concurrent. So these are concurrent processes. P1 and P2 are concurrent processes. Okay, now let's assume the situation. I'm writing the order of execution. So let's say this statement is being executed first, right? And let's say this statement is being executed next. Now after execution of second statement, let's say there is a context switching. If you are incorporating, imagine the scheduling algorithm, let's say round robin, and there is a time quantum. So after these two instruction execution, let's say time quantum gets over. That means next process, which is concurrently executing and residing inside the ready queue, will get the chance to execute, right? So let's say this P2 start executing. So the third, you are executing this statement of P2, right? So if you pay attention, initially I have taken the value of count as 10, and this 10 value is being already updated in R1, and R1 is updated. So R1 is having value 11 now. But here R2 is getting the value of count, and count is still 10. Okay, because this line was not executed. So this 10 value will be loaded inside the R2 here. Okay, and then let's say fourth, this statement is being executed. So because R2 is having 10, now R2 will get value 9. Okay. Now in case the context switching again happens, so the fifth instruction like this is executing. So when this statement will execute, the value of count will be updated as, because initially it was 10 and it is R1 was storing 11 here, so 11 will be updated. So here you can say R1 was having 11 value and count is 11 now. Now let's say sixth, this statement is being executed, and because R2 was having value 9, so finally the count will get value 9. So if I write final value of count, it will get value 9. Now you can check, there is a problem. If you are having a variable and initially the value was 10, if you are incrementing ones and decrementing ones, finally the variable must be having the same value. But here you are getting value 9. Now if you change the order of execution, let's say if we do not execute like this, if we change the order, so let's say fifth if you execute this and sixth if you execute this in the sequence, then here the count will be updated with value 9, and finally the value of count will be updated here with, because R1 was having 11. So this time the final value of count will be updated as 11, right? So if we decide some other sequence of execution of these, it may start giving some other result. So that means the order of execution of the instructions deciding the output or outcome. That means there's a race. Okay. So if you look at the definition, a race condition is a situation where the behavior of the system of the program depends on the order of concurrent event. So in whatever the order these statements are being executed, it is deciding the final outcome. That means there is a race. Okay. So please do remember, this is very important, right? So I'm closing this. See you in the next session. Thank you everybody for connecting.